Well, hello and welcome back. We're ready to jump in the saddle today and attack a new type of derivative. So our topic tonight, you can label it as deriving arc trig functions. Arc trig, also known as inverse trig, so you'll be familiar with seeing it, writing it, and saying it both ways. One of our main goals of tonight is just to slow down and just, recall how to evaluate an arc trig function, what its graph looks like, what are some of its special properties, its domain, range, etc., before we actually get into the deriving part of it. I do want to note in these three pictures that I did kind of steal from the internet, in arc sine particularly, these are not horizontal asymptotes. Okay, I want to be very clear, those are not horizontal asymptotes. I believe they just have those in there to show you that at 1, arc sine does officially reach a height of pi over 2, and at -1 it officially reaches a height of negative pi over 2. Likewise, in arc cosine, this is not a horizontal asymptote as either. I just want to be clear, do not draw those in your notebook. Those are not asymptotes. Again, it's just showing us that intended height. Now, however, in arctan, I do want you to take note that we do have two horizontal asymptotes at positive and negative pi over 2. And our goal, of course, by the end of the night is to be able to pick, let's say, a random point, perhaps at 0.5, and be able to write the equation of that tangent line on the inverse cosine graph. So like I said, let's get this sketched nicely in your notebook. We're going to focus on arc sine for just a few moments. And you'll remember that arc sine or inverse, when we talked about inverse back in Algebra 2 or pre-calc, wherever, we know inverse meant we kind of flip the x's and y's. Okay, so you'll notice now, instead of the pi over 2, negative pi over 2, etc., being on the x-axis, it's now on the y-axis. And our whole numbers are now on the x-axis. We flipped the x and y, so to speak. Now, this is obviously just a piece of the graph. If I flip the x and y axis, I hope you can picture this in your head here, our sine curve would have started to do something like this. It obviously would have went up, little jive and jab, swam maybe this way a little bit, and then it would have came down and went this way. Now you'll notice that that was not a function. Okay, so we did not pass the vertical line test, and what we had to do is we had to kind of cut it off and find a domain where this does pass the vertical line test so that it is a function. So we said basically if we kind of cut her off maybe here, okay, at positive pi over 2, and we cut her off at negative pi over 2, we now have a restricted domain, and this section in between my red lines here does pass the vertical line test and is a function. So I think we need to sum this up clearly on the side and say that our domain, if we're looking at our picture here, goes from -1 to 1, and our range, our y values, go from negative pi over 2 to positive pi over 2. Okay, now simply if you sketch that out, the domain and range are pretty straightforward. Now I think we need to clear up some algebra when talking trigonometry. For example, most people, let's get this in our notebooks nice and neat here, if we said the sine of pi over 4, almost everybody should be able to shout out the answer radical 2 over 2. Now again, let's focus on the terminology. This sine value is my x value, and that is an angle. Okay? This radical 2 over 2 is my y value, and that is actually what we call the value. Did you catch that? We keep calling it the value. So we typically take the sine of an angle and we get a value out. Now inverse sine, remember, does the opposite. It switches the x and y's. So if I say arc sine, okay, instead of saying arc sine of an angle, I'm going to say arc sine of the value, radical 2 over 2. All right, because I have to switch the x and y's. And this time I would give an angle in return. So the arc sine of radical 2 over 2 is pi over 4. Okay, so this time my answer is an angle, whereas if I'm just doing a regular sine, my answer is the value. Let's try a few more. If we said arc sine of 1/2. Okay, notice we gave you the value of a half, who is the angle when your sine graph equals a half. Okay, of course that's pi over 6. Now, again, instead of saying arc, we could have simply just said sine inverse of 1/2. Clearly those mean the same thing, just two ways to write the same thing. We get our pi over 6. Now here comes the nasty one. Okay, and this is the most missed one, of course, is when we say inverse sine, okay, or arc sine of -1/2. Now, your gut probably wants to give me some, number in the fourth quadrant, but be careful with your domain. If you were to go and graph -1/2 on your picture, okay, you can clearly see that that answer is a negative value. So your angle has to be negative something, okay? And I'm going to say that's negative pi over 6. Okay, so just be careful that you fall within your domain. Your answer has to be between positive and negative pi over 2. All right, so focusing on arc cosine. Again, you'll just take quick note that our domain, if I look at my x values there, that goes from -1 to +1, and my range goes from 0 to pi. So notice, let's just talk about that range. When you give an angle for your answer, make sure your answer is in quadrants 1 and 2. Okay, keep that in mind. Your answer has to be between 0 and pi. And again, if you know the graph, it makes the answer a lot easier. All right, let's just evaluate some values. Let's say, arc cosine of 1/2. Okay, so remember, this is the value. The question is, what is the angle? What is the angle when cosine equals 1/2? So hopefully you're thinking 60 degrees, which is pi over 3. How about arc cosine of -1/2? Okay, now again, the negatives are the tricky ones, but be careful. If you go backwards -1/2 on the graph and you go up here, you can see that you're in what quadrant? You're between pi over 2 and pi, which is quadrant 2. So basically, you need to put your reference angle of 60 degrees in quadrant 2. So 180 minus 60 is 120, which of course is 2 pi over 3. Okay, let's say arc cosine of 1. All right, so again, just look at your graph, go to 1, and we would say that has an angle value of 0. And let's go one more, arc cosine of -1. Again, I would go to -1, find my height, and that value is pi. Okay, so if you come in tomorrow and you don't know what the graphs look like, you're setting yourself up for failure. So perhaps this is the time you make some flashcards, but do what you need to do to have those graphs memorized. Now we get to our most popular graph, arctangent of x, or inverse tan of x. Now, by far, the AP loves arctan more than, all three of them. This is its favorite. So, I mean, if you had to pick only one to memorize, this would be the one, but, I mean, hopefully you know all of them. If you take a look at this function, and here's where it's a little different, the domain obviously goes from negative to positive infinity. Okay, it goes on forever there. And the range, you'll notice this one, is not inclusive. It goes from negative pi over 2 to positive pi over 2. But notice when I say not inclusive, it never actually reaches a height of pi over 2 because of this asymptote, of course. And this is the only function that has those horizontal asymptotes in it. Now with that in mind, we can answer some fun limit questions. Let's say the limit as x approaches positive infinity of f of x. And at the same time, we'll say, what is the limit as x approaches negative infinity of f of x? Okay. So clearly, as x goes out larger and larger, it's never going to reach pi over 2, but its intended height is pi over 2. And remember, that's all a limit is what is the intended height, the intentions of the graph. Likewise, if I go out to negative pi over 2, the intentions are that it will reach a height of negative pi over 2, although it never really will. Let's go through evaluating some trig functions. Let's say inverse tan of 1. Okay, so again, if I go out to 1, which we'll say is approximately here, I land on the graph there. So notice I'm in quadrant 1. I'm between 0 and pi over 2. And I would say that, of course, is pi over 4. The tangent of 45 is 1. And likewise, if I do inverse tan of -1, I'd go back to -1, find my value. Notice it's a negative height. Okay, my y value is clearly a negative height, and I'm between 0 and negative pi over 2, so I would say that's negative pi over 4. All right, we are finally ready to start some calculus. All of that was what you covered in Algebra 2 and Pre-Calc, and we're ready to dive into the rules. Now, we have 3 rules. They are a tad bit ugly, but with a little bit of practice, they'll be easy, just like anything else. So rule number 1, the derivative of arc sine of u. Okay, and remember that u is just a placeholder. Anything could be in there, x, 5x, 6x squared, whatever. Its rule is du over the square root of 1 minus u squared. Now, even though that's ugly, I think you'll like the derivative of arc cosine. It only changes just a tad, so it's kind of easy to remember. Because this arc cosine starts with a c, you've probably guessed it, it's just negative du over the square root of 1 minus u squared. And lastly, the third one changes quite a bit. The derivative of arctan, and again the most frequent on our AP it seems to be. The derivative of arctangent of u is du over 1 plus u squared. So notice we've done two things on arctan. We've thrown away the square root, so that no longer exists, and this minus under there has turned into a plus. So those are the three rules we're going to focus on for the next few minutes here. We're going to commit them to memory, of course, and you'll see these pretty frequently on our quizzes. Alright, so let's dive into some pretty basic ones. Number 1, y equals arc sine of 2x. So remember, this 2x is taking the place of my u. And if it helps, you can do a little work off to the side. We can say our u is 2x, therefore our du, take its derivative, is just 2. Now let's just apply the rule. Hopefully you kind of have it in your memory bank or flip back and look at it. The rule says it's just du, so my du is 2, over the square root of 1 minus u squared. Now the biggest mistake people make is just make sure you wrap that whole term up and square it, okay? I would just say this is 2 over the square root of 1 minus, make sure you square that whole term, 4x squared. And that's it. Let's try another easy one to get our feet wet here. Let's say y equals arctan of 3x. Alright, so again, just do a little work off to the side. I'm going to say my u is whoever I'm taking the arctangent of. My u is 3x. Therefore, my du is just a nice 3. And this time the rule says du over, so 3 over 1 plus the u value squared. And again, I'm wrapping that up and squaring it, so I get 3 over 1 plus 9x squared. Alright, let's keep checking here. Number 3, y equals arc cosine of radical x. Now notice I read it of radical x, but they're probably not going to put any parentheses in there for you, just like they don't typically on the trig. So when I read arc cosine of, put your own parentheses in so it's easy to identify that u. So again, I'm going to do this off to the side. I'm going to say u is equal to, and let's be smart and rewrite it. I'm not going to write radical x. I'm going to say x to the 1/2. Therefore, my du is 1/2 x to the negative 1/2, which is really 1 over 2 radical x. Alright, so now let's apply the rule. It's negative du, negative 1 over 2 radical x, all over the square root of 1 minus u was my radical x squared. Now certainly you're not going to leave a complex fraction and neither will any multiple choice, so let's just kind of keep cleaning that up. I could basically multiply the top and bottom by 2 radical x and 2 radical x. So I would get negative 1 over 2 radical x times the square root of 1 minus, this square and square root obviously cancel, 1 minus x. Now, you can actually go one step further. Let's just kind of review our rules for multiplying radicals. It's fair game to multiply radicals together. So I would say this is negative 1 all over 2 is on the outside, square root of x minus x squared. And we'll squeeze one more on this slide before we move on. Let's say number 4. Y equals arctan of, let's say, e to the 2x. So now we can apply our e derivatives that we've talked about last week. Let's say our u equals, what we're taking it of, e to the 2x. And watch that derivative rule. When I take the derivative of e to the 2x, I leave it alone and then take the derivative of the exponent. So I get 2e to the 2x. So my arctan rule is du all over 1 plus u is e to the 2x squared. Now lastly, we should be able to clean that up. Just think back to your basic algebra rules. Power to a power says you do what with exponents? Hopefully you just said multiply, so I would get 1 plus e to the 4x. We've got a pretty nasty one for you to play with here. We've got f of x equals arc sine x plus x times radical 1 minus x squared. And make sure you read that to yourself. When you say times, make sure you're doing what rule? Well, I think this is a great time for you to pause it, practice this rule we've talked about today, and maybe a little review there, and really try it on your own at this point. And then turn me back on and see if we've got the same answer going on. Well, welcome back, and hopefully we're on the same page here. There's my u is x, so my du is 1. I've got 1 over the square root of 1 minus x squared for my first term, which I thought was pretty friendly, plus, I'm going to say this is first, the derivative of the second is 1/2 my 1 minus x squared to the negative 1/2 times negative 2x plus 1 minus x squared to the 1/2 times my 1. And at this point, I'm just going to clean each of these up. And if you've got that, I think we're in pretty good shape. What I then did is I rewrote this. Instead of trying to get a nasty common denominator, I just said this is 1 minus x squared to the negative 1/2. My 1/2 and my 2 canceled, so they then got a minus x squared times 1 minus x squared to the negative 1/2 plus 1 minus x squared to the positive 1/2. And I said, okay, I can easily pull out a GCF, and that's what we've talked about all year. Every time you do product or quotient, pull out a GCF next. So I pulled out a 1 minus x squared, the smaller exponent is a negative 1/2. And so from this term, it's gone completely, but anything divided by itself is 1. This term, that's gone, so I get a minus x squared. And then I get one of these, so I get plus 1 minus x squared. So I've got, let's see, 1 plus 1 gets me 2 minus 2x squared all over the square root of 1 minus x squared. And I think that's cleaned up pretty nicely. All right, our last one's a little nasty. We're going to find points of inflection. So the first thing that jumps in my head, of course, is y double prime has to change signs of the function y equals arctangent of x all squared. Okay, so obviously I have to get my first derivative, so I'm going to slow down and take my first derivative. Let's see, so I got 2 arctangent of x, keep the inside, nice little chain rule, raised to the first power, times the derivative of the inside. Okay, and that rule is du over 1 plus u squared. And hopefully you can almost do this in your head. If your u is x, what's its derivative? 1 over 1 plus x squared. All right, now I'm going to clean that up, make it look just a tad nicer. Obviously, all of that's on top, a 1's on the bottom. So I've got 2 arctan of x all over 1 plus x squared. All right, now I need that second derivative. And I know we've been talking about, if you can avoid quotient rule at all costs, go for it. But I think we're out of luck and we just have to go with it here. So I've got my low 1 plus x squared times my d high is 2 times du over 1 plus u squared, so 1 over 1 plus x squared, minus my high 2 arctan of x, all over the the low, times 2x, all over my 1 plus x squared squared. And I think we'll want to clean that up quite a bit. And look what so nicely happens. The 1 plus x squared and the 1 plus x squared cancel. So I've got a 2 minus, I can multiply those, 4x arctan of x all over my 1 plus x squared squared. Okay, now I need to set this equal to 0 and solve. And at this point, we're going to use our calculator a little bit, and we're just going to type that in our calculator. So again, if you have that updated calculator, you need to pause it anyway. Go grab your calculator. I should have said that ahead of time. And we really need to practice working on that. Our next test will be calculator active. If you have that updated calculator, remember if you hit that alpha y equals, you'll get the nice fraction tool. If you have the old calculator, wrap the top in parentheses and the bottom carefully in parentheses. So I've taken some snapshots of what I've typed in and what I've gotten so you can compare with your calculator. So again, if you have that updated version, you get this nice division symbol in there and you don't have to worry about parentheses. When I hit my zoom 6, because I wasn't given a window to particularly look at, okay, zoom 6 is that standard window. This is the picture I got. I thought it was a little confusing, so I said I don't need all this wasted space here and here, so I just changed my window. I think I went from like +3 on the y to -3 for my y min. And then I said, okay, basically I'm making a sign chart. I'm saying this is f double prime, it's the second derivative, and I need to know when that second derivative equals 0. So I went and I found the zeros using that zero tool. So I had 0.6 0.765, remember 3 decimal places, and because it's symmetric, I also know that's going to be negative 0.765. I mean, I went and got it just to be sure, but it certainly is symmetric. Now, it looks like it might hit 0 again, but it actually doesn't there, and you can see that on your calculator. So up until negative 0.765, I'm below the x-axis, I'm above the x-axis, and then I'm below. So what does that tell me? I'm concave down. It tells me F is concave down, concave up, concave down. And I would say I have 2 points of inflection at negative 0.765 and positive 0.765. And that justification is F double prime changes signs. Okay, so we'll have more practice with the calculator in class tomorrow, and we'll look forward to seeing you then. Have a great night.